First, what is the composition of these different strata? Of course, you immediately saw that we don't have one kind of lithology, but we have different kinds of strata according to hardness, according to color, and as you will see, in fact, it's according to their main component: calcite, calcareous, or siliceous, silica, and also glaze. But this is the main thing we have to check. And if you remember, when we look at the composition of a sediment, simplifying, we may find three kinds of components. What we call the terrigenic or terrigenous. It means everything that has been brought in the sedimentary place, in the sedimentation place, brought by current, by water, by wind, but not in place. Second is what is due to life, so biogenic production. So it can be planktonic or it can be benthic organisms that are making some skeleton envelopes with silica or carbonate or calcite. I also put bio-induced because sometimes you find crystals of carbonate, for example. It's not due to directly produced by any microorganism, but it's induced because, for example, if you have what we call phytoplankton, which is making photosynthesis, it picks CO2 from the water, and if you pick CO2 from the water, you precipitate calcite. So you will make calcite. It's typical in many places. You have siliceous organism, but as they use CO2, they make precipitation of calcite. So it's strange, but you have the life is siliceous organism, but the sediment is calcareous. That's not directly a biogenic production, but a bio-induced. And the third component is what we used to call autogenic. It means some material, some crystal, some chemical product, which was not brought in the site by, let's say, a current, which is not due to production by organism, but which is growing, some crystals growing within the sediment after the deposition. So it's a third element. Here I will tell you what can be representing this kind of elements. And after that, you can address this main question. This is stratified. Why is it stratified? What is the reason? How we can explain the stratification? When I say stratification, is why do we have change? Why do we have limit? Do we have sharp limit? Do we have progressive changes? So that's a main point. What is creating the stratification? As you will see on the third stop, you will see a very nice stratification, but the explanation is totally different from here. So, going to this outcrop, if I forgot to bring chlorhydric acid to check calcium carbonate, so you have to believe me. I brought some vinegar, white vinegar from the hotel, but it's not so efficient. But if you look at this, mostly what is reddish, like here, it's pure silica. So it's siliceous strata. So the origin of this silica, I could only show you this with a microscope, because in the rocks you find remnants, we used to say ghosts, of planktonic organism, but making a silica envelope. which are called radiolarians. Maybe you know the word. So just a parenthesis. Tonight at the hotel we will sum up everything, and I will write a sort of debriefing and a PowerPoint that I will give you after. Okay, if something is missing. So radiolarians are marine plankton, microscopic plankton, marine with a silica envelope. If you look at some levels that are completely light gray, this is dominantly calcareous, so it's carbonate, calcium carbonate, but it's also very fine grain. You cannot see the size of the grain even with this small device. I brought two more, but not for this outcrop, for the next one. This is calcium carbonate, very, very fine. So same question, what is this calcium carbonate, which is the origin? It's highly recrystallized because they are old rocks, they have been compacted. But in this sometimes you can find a typical structure of calcareous nanoplankton. So it's also planktonic organism, but very small, few microns. Maybe you know some nanoplankton. Probably most of you have used nanoplankton. You know where you can find nanoplankton? If you take a piece of chalk to write on the board, the chalk in Paris Basin is 100% nanoplankton. So when you write on the board, you are just squeezing nanoplankton. So it's a tiny organism, a few microns. So it's difficult. It can be seen only with SEM, scanning electron microprobe. So two components, biogenic, siliceous biogenic, calcareous biogenic. Both are plankton. I can show you this directly because we should need a microscope and so on, but just believe me, and it's very, very fine grained. In some places, like there, you have more soft material, like this one. So what can be this material? It's softer, it's slaty. Yes, but with respect to the other, this contains clay minerals, and also some iron hydroxide. So this belongs to the third part, the autigenic material. But we will mainly discuss the limestones and the siliceous rock. But we also have some intervals of clays. Okay? So if it is stratified, it's because sometimes we sediment siliceous plankton, calcareous plankton, a little amount of clay minerals. So we have to explain this. That's one question. Of course, we will try to answer also this afternoon all together, but this is one question. Of course, we have first indication. Most of this is made of plankton, siliceous or calcareous. So plankton is just a production in the upper part of the sea. If you have a planktonic organism made of calcite, if it goes down through the water column, what can happen to this tiny organism? Some of you know what can happen if the piece of the calcite is going too deep at 3, 4, 5,000 meters deep. Because, of course, all this is marine. What can happen to some calcite crystals going down? Yes, it can be dissolved. Because sometimes in deep marine water, deep oceanic water, the chemical characteristic of the deep water is that it's undersaturated with respect to CaCO3. So the CaCO3, the calcium carbonate, is dissolved. So there is a competition between what is product and fall down and the dissolution. And that's why we have a depth usually called the CCD.
I think a car is coming.
Oh, that's okay. The CCD, which is carbonate compensation depth. So it means a depth, water depth, where below you won't have carbonate. But if you produce silica, of course, if these pieces of silica, this tiny silica skeleton fall down, there's no problem. They can stay at 4, 5, 6, 7,000 meters deep, preserved. But there is a main difference, is that a siliceous organism, when it is in the upper part of the water, close to the surface, there the water is highly undersaturated with respect to silica. So if a tiny skeleton of a radiolarian stay close to the surface, rapidly it will get dissolved. So you won't have siliceous sediment. So the only way to have is that at the difference from the carbonate, you need a high production in the surface, and you need this production to fall very rapidly, because if it stays in the upper water, it gets dissolved. So it's a different behavior. So this is interesting, and that's why we have to discuss. When we have a pure siliceous rock, the reddish one, and when we have a pure calcareous rock, we know that the planktonic production is different, and you know the condition of preservation have to be satisfied. So that's one of the questions we will discuss this evening. Why do we have these changes? And in some parts it looks like these changes is rather rhythmic. You know what I mean by rhythmic? I have not said cyclic. Next we will begin to talk about cycles. But now we just say rhythmic. Clay, ferruginous clay, calcareous level, siliceous level, and so on. It's a sort of repetition of rhythm. So we will have to discuss why we may have this rhythm. We know what is changing. Basically, we have to change the production, the planktonic production, and we have to think about why the planktonic production is changing, and is it changing fastly? Because one tiny strata of silica, like this one, may be a period with a high production of radiolarians, of siliceous plankton. But what time? What duration? How many years? How many thousands of years? So that's the question. If we have sort of rhythm or sort of cycles, the interesting point is to know the time length, the time span for each cycle. And this is very important, not only for sedimentology, for paleoenvironment, because when you use sediment thicknesses to discuss fault displacement, you need to know the sedimentation rate. So you need to know, if you have 100 meters of this, you need to know the time which is represented, because masses of sediments are used also to calculate, to estimate fault displacement. Okay? So you please check the outcrop. Well, strata are vertical. Here it's not exceptional because everything is folded, but at least we have a small outcrop with 15 meters of continuity. So I have we don't need this because we cannot see any component. It's too fine grain. But just look, I have a hammer. At least you can prove that some of these radiolarian strata are pure silica because it's harder than the steel of the hammer. That's a very old system to detect silica when you are in the field. You just scratch the hammer.